So what you'll go through and do with your Ka monoprotic acid data is you'll go ahead and enter it into Excel. Okay, really we only need 2 columns. Trial doesn't really make sense, but whatever you want to do. And you will have a volume of NaOH with a pH, and you'll just enter all of that data in there. Okay, we're going to go through a series of calculations to refine this data. So you will continually be referring back to these cells, just kind of be aware of that. But what we'll do first is take a stab at getting this plotted. So we can go to Insert Charts. This is going to work with me. I would recommend the straight marked scatter plot. Okay, everything that you're plotting in this class, you should be using the scatter function if you're using Excel. Okay, if you use any one of the other functions, Excel is going to interpret your data in a way that does not make mathematical or physical sense. Okay, so make sure you're using the scatter functions. I'd recommend just the straight line. Sometimes Excel likes to decide that it wants to plot everything for you. Since I think that's a lot of crap, we're just going to delete it all. Okay, so in theory we should start with just an empty graph screen. What we'll do is now add a series. In this case we're looking at just your pH titration curve, so nothing fancy. On your x-axis you want to put the independent variable, so the one that doesn't change. That's going to be your volume. Okay, so we can put our little cursor in the x values and then go back to our Excel sheet and click and drag for our volume values. And then for the y values, Excel likes to say all the values are 1 at first, so you just got to go through and tell it that you don't want that. And then you can click and drag your pH. So your pH will go on the y-axis, your volumes will go on the x-axis. At this point, you now have your pH titration curve. There we go. And it looked exactly like what you had before. Okay. I think the legends are absolutely useless. If you want to use them, by all means go ahead and use it, but it's pretty pointless. Okay. So now what we'll do is make this a little bit bigger so we can see it a little bit cleaner. Some formatting tricks, particularly as it comes to reports. Every single graph needs to be fully explained. So in your report, at the bottom of this, you'd give it a little caption describing what it shows. So this would be Figure 1, pH titration of an unknown acid against NaOH. Okay. The next piece of information you should include along with this is the information you're trying to get off of the graph. So why are we plotting all of these titration curves? What's our goal? What are we trying to get off of it? The equivalence point, and then ultimately the half equivalence point. Okay? So what we're going to go through and do now is look at all of the intricacies of determining the equivalence point. So the easiest method, actually before we even do that, let's make sure you guys know how to put your axis labels on. We can go to Chart, Layout, Axis Titles. We'll want a title below the axis. That would be our volume of NaOH. In theory, you should always include your units. I don't think I'm going to get too strict on that, but it should be there. And then on the y-axis, I prefer the rotated title, but it's not that big of a deal. Y-axis would be your pH, and we don't have any units for that, so we've got our axis on there. Any questions about any of that so far? Nice and simple, right? Yes?
How do we know which one of ours is better?
You'll know which one of yours is better by looking at the data. So once you plot the data, you can interpret it. Our whole point is to get the equivalence point. That's our goal. So that equivalence point is going to show up when we, let me zoom in on this a little bit actually. That value we're going to be doing lots of playing around with the axes in a little bit. Okay. That equivalence point shows up when we've added enough base to completely react with the acid, which means what happens to the pH. When when we completely remove the acid, what happens to our pH? It spikes. So what we're looking at is the exact instant where we've removed all of that acid. So it's the midpoint pretty much of these two. It's that vertical line. So our equivalence point is roughly the dead center of that. Alright, so as far as whose data is better, who has more data points on that vertical line? The more data points that are on that line, the better your data is going to be, the easier you're going to be able to interpret and determine what your equivalence point is. Okay? If both of your data sets have no data points on there and you're really not happy with how your curve looks, then you can go through and run it a third time. I think we'll be able to work with what you've got. Okay? I don't think anybody's going to be in a bad enough situation where you need to do it a third time. Okay? Ideally, you would be in the situation that we've got with this data. You see data points pretty much all the way running smoothly up, which smoothly turns into a curve, and then smoothly turns into a curve the other direction. So it should be nice and smooth all the way through it. If you get jumps or breaks in it, that's not ideal, but that's what happens. Okay? It just comes down to how careful and slow you were through this. So not to point fingers and name names, how slow did you take to do this?
An hour or more.
Yeah. So if you were taking roughly an hour or more to run your pH titration, your data should look like this. If you're taking less than that time, your data probably doesn't look like this. If you took less than 30 minutes, it's probably not very nice looking. Okay? Most of it comes from experience. If you haven't had the experience to see what's happening with all the spikes or where the pH spikes, it's not going to look as nice. Okay? I'm going to guess this was the second trial. Yeah. Okay? So that's why we kind of staggered the two people doing the titration. This is the first person could go through, find out where the pH spiked, tell the second person to make sure you get a lot of data points through there. Okay, that was our goal. So as far as figuring out our equivalence point, the first thing that we could do is we could just say, well, halfway in between here looks like about that value. Okay, then I can eyeball it straight down and say, that's roughly, I don't know, 16 milliliters. So the equivalence point is at 16 milliliters. Okay, that is one method to do this. That is very coarse because we're just guessing ultimately at where everything's at. We don't have enough data on our x-axis or our y-axis to really kind of zero in on that. So what we can do is now zoom in, albeit very painfully, into that range to try and determine where that half equivalence point is, or sorry, the equivalence point is. Okay, so to do that, what we're going to do is change the axis, change the axis values so that we can see just in this range, which means I only want to go from roughly 13 milliliters to, say, 18. So to zoom in on Excel, as stupid as it may be, we can set our minimum value to be 13 milliliters, our maximum, what did I say, 18? 18. If we move that box out of the way, we can now see that line a little bit better. Okay, so we can see a little bit cleaner. We can even get a little bit more accuracy on our x-axis. Because I've now zoomed in, I can also now adjust the major unit demarcations so that I can get a little bit more data. That looks a little too small, so let's try that. Okay, so what we'll do is adjust that so that we can easily read it along that axis. Okay. So that helps, but now the graph is kind of floating in the middle, so what we'll do is adjust the y-axis as well so that we can again zoom in a little bit better. We're running probably minimum value. I'm going to go 8 and 11. So, since this is your data, you guys get to decide. Where do you want to call the equivalence point? Here, and I'll start a little marker here so you can see me move along it. Okay, I will start at the very bottom and slowly move upward, and you can tell me where when we've reached. Come on. Okay, so that's where you're calling your equivalence point. What we need is the volume at that point. Okay, we can cheat in this in a couple ways or help us see that point. What I would do is go back to Excel. Where's my thing? Shape. Draw a line roughly straight down. Say the volume's at between 17.7 and 16 milliliters. So we'll call that 17.8, if you will. You know. We could go through and add in more grid lines as well as if you wanted. That's entirely up to you. Yeah. Okay. At this point, this is a very coarse guesstimation estimate, pretty much just raw guess. Okay. This gives us our equivalence point. How would we get the half equivalence? Cut that volume in half, so we would shift to 8 milliliters. So what we would now need to do is adjust our graph. So we can write down, first off, our equivalence point, because we'll come back and make reference to this. So we said 15.8. Is that what you guys want to use? Okay. So we'll zoom back out. Format axis. I want to get down to that 8 value, so my minimum, I'm going to do a 6, maximum 10. Is that right? We said 8, yeah. Our major unit, whoops, 0.2. In that range, we're probably at a pH close to 4, I think. Yep. Look at that. Good guessing. So we'll call that pH 6, pH 5. To a maximum of 8. Can take my little straight line marker. We said half. So we're somewhere in here. Extend this upwards. I'm now at the half equivalence point. What's special about that point? How does it give you the pKa? The pH at that point gives me the pKa, so I'll switch my little silly marker. Slide this up. The pKa of your acid is roughly 7.1. So all we're doing is just looking at the graph and trying to interpret that data. Okay? We'll go through a little bit better of a version on the half equivalence to get that pKa once we have a better understanding of what the equivalence point is. Okay? Does that make sense? Any questions about that so far? So all we're doing is using that pH curve and directly interpreting off of it. Okay? The next part of this is to go through with some other mathematics. Okay, so we'll zoom back out. Okay, so what we can do is go back to the lab procedure. Do I have it? Yes.
The lab report, do you have to show like those different graphs? So like
The lab report will have at least 3 graphs.
So like the overall, from the same thing to show a different.
Oh, the zoom-ins? No.
Okay,
No.
so just show the overall.
So what I would expect for your first graph would be this. Just your pH titration, no zoom in, none of that. You would write in your figure or your caption for your figure what your equivalence value was and what your half equivalence was. Okay? So you're going to give me that interpretive information off of that curve, but you do not have to zoom in on it to try and get that all figured out. No. Good question. So what we just went through was to determine those values. And you'll notice that if we look at the lab procedure, the data analysis has you go through, calculate the molarity. I'm going to assume you guys know how to do that. If you got questions, you can ask. It then goes through and says use high quality graph paper. Excel is high quality graph paper, so you can ignore that. And then they start to talk about plotting a first derivative, second derivative, or grand plot. Okay? Those of you, or how many of you have taken calculus? Let's try that first. So we got a few of you. What is a derivative? It's a rate of change. It's the slope of your line. So what we can go back and do is look at your graph. And what we're trying to determine is that equivalence point. What is special about that point? What happened at that point? What are you saying? So if we look at the slope, if we calculated the slope with, like we said, a first derivative, and we go through and take a look at our slope, relatively low, and then all of a sudden what happens as we get to the equivalence point? Shoots straight up. Then what happens after we pass the equivalence point? Levels off again. So what we could do is plot a first derivative, where we measure the slope of the line at several data points, and the equivalence point is going to be where our value peaks, okay, where we get a maximum value in the slope. What we're trying to interpret is what's known as the point of inflection. I think it's the point of inflection. Okay? If we take a look at our curve, this portion of the curve is concave up. What about the other portion of the curve? Concave down. So what we're looking at is where our data ends up swapping directions of facing. God, that was awful. I hope no mathematician ever listens to this. Okay? So mathematically, all we're looking at is for derivatives. We can look at the slope to say, okay, that's where it's going to peak. That, in theory, will be easier to identify than looking at this data, where we're just guesstimating where it's switching. Does that make sense? Okay. So to do that, we now need to determine the slope. Okay? And because we're going to do a couple different graphs, I'm going to add some titles to these. These titles are solely for the benefit of setting these up. I do not expect titles on any of your reports, okay, or any of the data that you give me. I expect a caption at the bottom that describes it that would incorporate everything that the title would say. So there's no point in duplicating it. The only reason we're using it here is so that we know what we're looking at. So this is our pH titration curve. And since we're now not going to interpret this anymore, sorry if this makes you dizzy, move that away. We now need a slope. Okay? How do we determine a slope? Rise over run, so the change in the y value over the change in the x. So what we're going to do is generate some new data. We'll call this our first derivative, okay, and this will be our new y value. Okay, so our y value, or our slope, is the change in y. Which was our change in y? The volume or the pH? The pH. So what we'll go through and do is we'll look at the difference in our pH across those two data points. We then want to divide by, what is it? Rise over run, our change in x. What's our change in x? It's our our volume. If we went through and just entered it as is, we're going to get some pretty awful numbers. Okay, why? Order of operations. We need to make sure we get our parentheses in there to make sure Excel knows how to calculate. Whoops. Okay, so this will give us the slope of our line. We can click and drag and have Excel calculate that all the way down. We'll check just to make sure it's doing it right. Yes, it's still calculating the last two values. Okay. Next part about this, we now have a new y value, but we need an x value. What is the volume at this point? Is it 4.42? Or is it 4.04? It's the slope between those 2 points. So what volume should we use? Yeah, we'll use the average of those two values. Okay, so our volume for that data point will be our average. Okay, and we can do it manually by entering it like this. We'll look at how we can make Excel do it fancy-wise with another data point later. Okay, again, click and drag. Make sure it entered it or calculated correctly. We are looking at that for our last data point. I did the average. I did the average of the pH. Sorry, that should be the average of the volume. Is that what you were about to say, Union? Sorry, we need to make sure that's the average of the volume. Yeah, because I did the average of the pH, not the average of the volume. It's got to be the average of the volume. Okay. Other questions on that? Thank you for catching that, by the way. So this will be the first derivative. This is our y-axis. And we'll call this our first derivative x-axis. Expand that out a little bit so we can see it. Okay. One more thing I want to kind of ask so that we could interpret our data. What happens to our slope? So let's ignore the beginning part at first, because it turns out your acid is actually diprotic. Okay, so let's ignore that initial part. What's the slope of our line? Big or small? Small. So relatively no change. So as we look at our data, we would expect a very small slope, very close to zero. And then what happens as our experiment goes? Slope picks up. So if we ignore again those first, how many data points did you take at first? Like 10 data points, we can ignore those. We can take a look at our slopes. We would expect a relatively small slope, something very close to zero, then followed by a spike. So let's go back to our slope data. We ignore our first series of data points. Okay, 0.5, 0.3, relatively small slopes until what happens? Take a look at the numbers. They end up spiking. 2, 9, 2. Okay. So just a superficial analysis of the calculations suggests that we've got something correct. So what we're going to do again is, because interpreting raw data is not the easiest, we will go through and plot the data. So again, we want to insert chart, same idea, straight line. Oh, mother. Again, I have no idea what Excel is doing, so I'm just going to delete all of it. Okay. X values, what did we say was our X? Our change in volume. It's a good thing we labeled it, so we now know which one it is. Our Y values, again, we have to make sure to delete that 1. This is our column next to it. And we've got our Y values. So as we just described, what we would expect to see is relatively flat, then peak, and then flat again. Okay? So let's see how we did. Take a look at that. We do see 2 peaks, interestingly enough. Why are there 2 peaks? Particularly with one right at the very beginning. The only reason we would see a peak is if we had an equivalence point. Why would we have an equivalence point?
Did you say theirs was di?
There's an acidic hydrogen there. Okay? So it turns out that your unknown acid is a diprotic acid. And that when they gave it to you, the unknown, it still had some of the diprotic species in it. That's what we're seeing at the very front. Okay? We don't care about that value. In theory, you shouldn't even see it. Okay, so there's a few of you that have that kind of showing up on there. You can ignore it. Take a look only at the other section. So what we would want to do is take a look here and say where our peak is. It says 15.8 milliliters. What did we say was the equivalence point?
16.
Roughly 16 milliliters. Hey, look at that. It actually worked out really well. Okay. Should have asked for somebody else's data because I think your data has too many data points in it, which means it's going to be easier to interpret. No offense. So what we'll do is go ahead and zoom in on that range so that we can see it a little bit cleaner. So we'll format our axis again. We'll make the minimum, I'll go with 12, maximum 20. So now that we can see that peak a little bit better. Okay. This would then be our first derivative plot. So let's go through and we would go through and add in all of our axis labels. I'm not going to do that because I'll leave you guys to figure that out. We'll put in the title charts that we know what we're referring to for our own sake. We're looking at the first derivative. Okay. As far as how we interpret this graph, what we want is the peak, okay, where our value absolutely peaks. You'll notice that you will have a data point at a peak. Is it the peak? Not necessarily. Okay? You have data points that are falling on some line which may not necessarily be the actual value. So we will see this spike upwards, but our peak could be slightly off of it. Okay? And you just happen to get the last data point before it spiked upwards. Okay? So with that, we could say that more than likely we're really, really close to it. We're somewhere between those last two data points, this one and this one. Okay, your equivalence point is somewhere in there. So we could look at those two values and we would say 15.81 was one value, the other value was 15.86. Your equivalence point is somewhere in between there. Okay? So that's a lot better than just guessing off of our pH curve, but it still leaves a little bit of ambiguity. Okay? So with this curve, what I would expect is this zoom in so I can see it a little bit cleaner, because the rest of it I don't care about because it's just going to be flat. You would give me this first derivative plot, you'd give me the axis labels, and you'd give me the figure caption describing what it is. Shows the first derivative plot of our pH curve, and what information do you get off of it? The equivalence point is between 15.86, is that what I said? 15.95 and 15.81. Okay. This could mean the half equivalence is this, the pKa would be this. Okay? So that you're interpreting some information from it. Questions about that? Okay. The next part of this is saying, okay, we're again just kind of guessing approximately where it is. So we want a more definitive value. Okay, so let's go back to our first derivative curve and say, okay, we're trying to get that peak. What can you tell me about that peak? So let's go through and draw a curve in on top of this. Let's say it looks something along these lines. So let's say you missed it. Okay, you didn't get it exactly perfect. What can you tell me about that peak value? This goes back to those of you being calculus, having had calculus. The derivative of this data is 0 at that point. Okay? As we go through and interpret, we have virtually no, or we have a 0 slope. Then all of a sudden what happens is we get near our equivalence point. The slope, or the rise over the run, all of a sudden spikes. Okay, so we go from having virtually no slope to now having a positive slope to what happens at that very point. It has again no slope, and then what happens down the other side? We now have a negative slope, which then goes back to a 0 slope. Okay, so what we'll do now is look at a second derivative plot. Okay, so a derivative of the first derivative. Why is that going to be helpful? Well, we can look at the value where our data crosses the x-axis, because we go from being a positive value to all of a sudden being negative. How do we transition from positive to negative? You go through 0. And once we cross that axis, we know we are at the equivalence point. So that will be able to, or allow us to interpret our data much more definitively. We can see much more cleanly exactly where it crosses the line, and we can get a better equivalence point value. Okay? So how do we go through and do that? Well, the first is we'll get rid of our first derivative plot, move that out of the way. And we'll now go through and deal with our second derivative. Again, we'll call it y first. We want the slope of our first derivative. So what we'll go through and do is say the rise, which is our y value, difference in y. Again, we want to watch out for those parentheses because we want it, order of operations to be appropriate, divided by the change in our run. Whoops. Oh my gosh. Let's see if I can keep typing different buttons. And we now have the slope at that value. Again, click and drag to copy this data all the way down. Okay, and we can go through and again do our x value. Okay, for our x value, what do we want to pick? It's the change in volume. Which change in volume? Our first derivative change in volume. Okay. Again, we want our average there, so we'll do an average this time. I can select the data. Now we've done a really fancy way. Same thing as if we added and divided by 2. Again, click and drag. Okay, remember we said that theirs was a diprotic acid, which made this a little bit more difficult at the front end. So let's ignore the front end of the data. So let's ignore all of that. And now take a look at the slope. Okay, the slope at the second derivative. Okay, so let's now start looking at those values. What are those values? Big or small? Very small. They're all hovering around the 0 slope. What happens as we continue to go through the data? Our value spikes and gets very, very large, and then goes negative. And then it goes back to being relatively 0. Okay? So at first blush, this looks pretty reasonable. So let's go ahead and set up our chart. Again, straight march scatter. Thankfully, I didn't put everything in on this time. Select data. I want to add a series. Our x values. And our y values. Now hopefully when I click OK, we see something along those lines. Again, remember that initial point is going to mess with us a little bit, so we can ignore that. Yes?
I missed what the x and y values are.
Those are, the y value is the slope of our first derivative. So the change in y of our first derivative. So if we go back and look at those cells, what we're doing, oh, didn't show that. So you can look at the formula at the very top. Q8 minus Q7. So the change in y for our first derivative divided by the change in x for our first derivative. That would be the y value for your second derivative plot. Your x values are the average of your volume for your first derivative x values. Same thing as we did before, I just used a formula for Excel to import it. Other questions? Load this up a little bit more so we can see it. Most of this is going to be pretty useless for me to see as a graph, so what I would like again is for you to zoom in on the appropriate area. So where I would zoom into it first would be so we can get a kind of a feel for it. Would do 12 to 18. And now we can see a reasonable value. I change the y-axis a little bit here too so we can see that. Let's just try 100. That'll be okay. So this would be the plot that I would expect to see in your report. And you would call this your second derivative and start to interpret your stuff off of it. Okay? That's what you would show. Before we continue on, let's go ahead and actually get what we should officially interpret off of this curve. Okay? This is where I would pull data from for your equivalence point. Okay? Because this is the least error-prone method to getting that data. Because what we're looking at is where the data crosses the x-axis. It's the easiest place to find it. We don't have to stress too much about it. Okay? So again, where I would go through and do with this is zoom in on the axis to make sure that we're looking for that crossing. So I'm going to change this x-axis. Make this 15.5. And because I want to be able to interpret more information, I'm going to change the major, man, this gets in the way. Change the major grid lines. Let's try 0.5. 0.2. Nope. Too many. 0.5. We can read that. Okay. So where do we decide is the crossing? Becomes the next big issue. Okay, well, where our y value equals 0, but I see one here, and one here. Where do we decide? Any ideas? One of the problems with this is that your data through there is going to be rife with error. Okay, a very small change in the volume can make a very large change in the pH. It becomes more difficult to interpret. We want where we get the most dramatic shift, which in this case would be here. Okay, so I would pick that value to be the crossing. Okay, so I'm going to zoom in even further on that range, if I can. And now we can interpret a lot more information about that exact crossing point. Somewhere between 15.78 and 15.79. So what we're looking at is that value. What do you guys want to call it? It's your data. You get to call it. You can leave it to the rest of the class too. They can call it for you. But you guys can be mean and call some random number so that when we go through and do their calculations, they're all wrong.
All the numbers. Okay, 50 point. I guess the line. Is it the
This is 7.8. This is 7.9.
7, 8, 7? Oh. 17 or 15. I can't read that.
I guess it's not as zoomed in on your screen as it is on mine. So it's somewhere between 17.78 and 17.79. So you can take whatever number you want to include on that. I would say it's closer to the 15.79.
So like, let's see, like 780.
Okay, there we go. You now have an equivalence volume. Okay? Compare that back to our other volumes. What were the other numbers that we started with? Our very first one was 16-ish. What was the second one? 15.8. We're getting progressively more or closer and closer to the actual value. Getting a little bit more information or accuracy off of it should be a better result.
So do you want us to report the equivalence points for each graph?
You should report them for each graph. You will not have to calculate for each equivalence point. So you'll just pick the one that you think is the best, and that will be the one that you will calculate. Okay? So at this point, I kind of want to open it up to questions about what's shown up here before moving on with any of the calculation. So as far as your calculations go, before you should even show all your pH titrations, you should have the calculations for your molarity. Okay, what I would expect is one example calculation for a molarity, and then give me a table. You don't have to get too fancy with the table. Trial number 1 to, I think everybody here, yeah, should have 4 trials, and then the molarity. Determine from each trial whatever those values are. Very last thing in that table, average, blah. Okay, does that make sense? Nice and neatly organized so that I can see what you're trying to show. Okay, then you'd go through with your 3 graphs, or your 3 figures. So you'd have figure 1, which is your pH titration. Then you've got figure 2, what was that, first derivative? I'll erase that real quickly here. One thing you should avoid doing is using abbreviations. So you should write out first derivative, not do 1 ST, just saying. Figure 3 would be your second derivative. If you want to go through and do a 4th figure, you can. It's known as the grand plot. The lab procedure gives you explanations on how to go through and do that. It's entirely optional, up to you if you want to do it. Okay? I'm not going to make you do it. Each of those figures should tell me what the equivalence point is. Okay? And our sig fig should get increasingly more accurate as we go through those. Okay. Ideally, you should also list your pKa from each of those versions. Okay. At the end of this, just out of curiosity, we've got 3 different methods for determining our pKa's and all of that fun stuff. Should you average these pKa's? Why is it a bad idea to average them?
Each one has a different level of error.
They're all different levels of error. Okay? So they all may be giving you similar results, but averaging them only increases the error in your best analysis. So your second derivative gives you the most accurate value. If you decide to average in your guess, you're taking all that work and effort that you put into making a really good value, and you're now making it crappy. Okay? So do not average these. Okay? The only times we can average is when the error between those trials that you're averaging is all roughly the same. Okay? So at this point, we'll have all the graphs, you'll have your calculations for your molarity, and everything will look nice and neat. Then you can go through and start with the actual calculations for the report, which is getting the molecular weight, which I'm now going to erase all of this so I've got a little bit more space. We'll cut this in half. We'll have our equivalence point information, So the equivalence point leads us to the molecular weight of the compound, or the molar mass, and then the half equivalence. Wow, sorry, that says equivalence. Will take us to our pKa and Ka. Okay? So, what do we get, or how do we get from each of these things? What kind of calculations would I expect? So the equivalence point takes us to the molecular weight. How? What did we do to get to the equivalence point? Titrated what? Be a little bit more specific than that. That's a little bit better. Maybe I heard it, or maybe it was just a sigh. The weak acid. So we've got our weak unknown acid titrated against what? A strong base. Because we have a strong anything, are we looking at an equilibrium? No. We get a direct one-for-one reaction. We would get A minus plus H2O. This means all of the calculations from this point forward are not 152 calculations. These are 151 calculations. Okay, as far as your molecular weight goes, it's all stuff you've already done and seen in 151. What do we know about the base and the acid? We know the molarity of the base, which was approximately what? Did you guys actually calculate it? Yeah. When I say with a long pause, you didn't calculate it. So you would go through and take your calculation. You said 0.125. Did you just give me a number? I'm not hearing anything you're saying. So, the molarity should be to 4 sig figs. Just throwing that out there. That gives you a molarity, so you know that. What else do you know?
The ratio.
I believe what you're getting at is the mole-to-mole ratio. The moles of acid related to the moles of base. What is that ratio? 1 to 1. How do you know it's 1 to 1? Balanced equation. What else do we know? We know the volume of NaOH added. What is that volume? This is the calculation at the equivalence point. How did we get to the equivalence point? We added whatever volume our results went through and told us. So in this case, you guys, what do we have? 15.788, I think is what you said. Milliliters. Do we know anything else? Yep. Well, no, it's something else. What did you say? pH isn't going to help us here. But yeah, we do know the pH at that point. That's in our molarity and volume. We'll come back to what else we know. Close, not quite. We'll come back to what else we know in just a second once we start to crunch out these calculations. So at the equivalence point, okay, I know all that 1-to-1 ratio and stuff, and I also know how many moles of NaOH there are. I can calculate that based on that information. I can take the volume of NaOH added, convert it to liters. I do not recommend that you convert in your head like I just did, because typically you do it wrong. I'll do it wrong as well. Times our molarity, which was 0.1253 moles of our base per 1 liter. That gives us the moles of base, What do we know about the moles of base versus the moles of acid? 1-to-1 ratio. What did we just determine based on this calculation? The moles of our unknown acid. That's kind of helpful. What were we trying to get to? The molar mass, or the molecular weight. What are the units on that? Grams of HA per moles of HA. Do we know the moles of HA in that solution? Yep, we just calculated it. So this number can now swing down into this. To figure out our molecular weight, we need to know the grams of HA that we started with. Is that something that we measured? Yes. So the other thing that we knew way back at the very beginning was that you knew that you started with roughly 0.4 grams of your unknown acid. You should have that reported out again to 4 sig figs. Slide that number in down here, run the calculation, and you now have the molecular weight of your unknown acid. Okay? Questions about that? Okay. What do we do at the half equivalence point? These calculations are really fun because there really isn't anything to do. Okay. How do we get the half equivalence point? Equals our volume, which we said was 15.788 milliliters, divided by 2. We now have our half equivalence volume. Woohoo! What do we do with that? Go back to the graph. So all you have to do is now look at the graph at that value and tell me what the pH equals. So at our half equivalence, pH equals pKa. We'll go pull it off the graph here in a second, get it super accurate, and you're done. Well, almost done. That tells you the pKa. The lab asked for the Ka. How do you get the Ka from the pKa? 10 to the negative. In this case, we'll go pH here, which is the same thing as our pKa. Now you've got the Ka to report, you've got your pKa, all those fun things. The last part of this report, because I believe it's title, methods, results, and discussion. Am I right? Is that what you guys are supposed to write? So your discussion and conclusion. What should show up in your discussion and conclusion? Kind of introduction stuff. You need to be careful with that, though. So I'm noticing a lot of people just rewriting an introduction. I don't care to read it twice. The whole point of a discussion is to discuss what? Your results. So the very first thing you should start your discussion and conclusion off with, your results. Okay? You could say 3, but it's really 2. The molecular weight and your pKa or Ka value. So you can go through and discuss those results. And in particular, how information back in the introduction or your calculations either lends credence to your values being good or bad. Okay? So you could go through and discuss why you decided to use the second derivative plot. Okay? Well, why did you not use the pH titration from the get-go? What did we say we were doing when we got the equivalence point off the pH titration curve? Rhymes with yes. Starts with a G. Guessed. Okay? Why would we not guess? That's how people die. Okay? So we're not going to guess at our results. We're going to go through and try and nail it down as specifically as possible. So we will go through and do the first derivative plot. Why did you decide not to use the first derivative plot? It's a little bit more accurate, but we could do better. So we then moved to the second derivative. Why do we use the second derivative plot and not the grand plot? Really, because you were lazy and decided not to do the grand plot, which is fine. But it's the best set of data that we can get out of there. Okay, it's the most accurate version from what we've done. Okay? If you decide to not use the second derivative plot, I'm fine with that. But then when you get to your error analysis, you shouldn't tell me that your results are perfect, because you guessed. Okay? Yeah. It's a bit dramatic, I guess, right? Okay? At that point, you can kind of go through and summarize maybe a little bit more, but you kind of run out of things to talk about because you don't have anything to compare to yet. Except you talked to me, right? And you got the unknown values. So by the end of today, you should come by and say, hey, this was my unknown number. What was my molecular weight supposed to be? What was my pKa supposed to be? I will give you those numbers so that you can directly compare and verify, yes, you did really well, or yes, you didn't. No, you didn't do very well. Okay? So if you did not get those numbers, talk to me after we finish here, and we'll finish, or I'll get you that information. Okay? So the last piece of information I want to end with is getting that pH pKa value. What we'll do is go back to the Excel file, and I'm going to scroll down to our pH titration curve, and we're going to again change some axes. What did we say was the... We didn't calculate the half equivalence. What was 15.7, whatever it was, divided by 2? 7 point... Okay, so we'll go 7.4, 7.7. We can read that. Change our pH as well. So, I guess we could add the grid lines. What did we say was 7.56? Something there? There's our value, or there's where we hit our line. We would then slide across to our pH curve. You can zoom in a little bit better there. That's good enough. 7.56. We are 7.039. Okay. At that point, we are at the half equivalence, which means that pH value is your pKa. Does that compare with what I've told you guys already? Did you already get what I told you it was?
Our pKa was 7.2.
And you're at 7.04. Okay. Pretty close as far as what you guys will end up getting. Okay. Questions about any of that? Okay. Then I've got nothing else for you. I will go ahead and post